Thanks for joining us today. My name is Josh Reicher. I'm a senior engineer here at Analytical Graphics. And lately we've been talking a lot about digital mission engineering and putting the mission at the forefront of your mind when you're starting the design and concept processes for any new product or system design. So today what I'm going to be walking you through are all the different options that are available to you to actually integrate your models into the STK operational environment. So today we're going to be talking about connecting your models to the mission. So first and foremost, I want to talk about what do I mean when I say a model. So there's a lot of different types of models out there, and they come in a lot of different flavors and a lot of different form factors. So when we talk about models, we're talking about pretty much any sort of digital artifact that describes a component or a system. So this can be things like aircraft performance models or sensor payload performance. We do a lot with communications and RF propagation. And then, of course, the environment that all of these things exist within. So the terrain, the RF propagation environment, and all the other kinds of things that are around the objects in your scenario. And these models come in, like I said, a lot of different form factors. So in some cases, you're just provided a list of numbers. So on this slide, you'll see like an Excel spreadsheet. So most of you are familiar with key value pairs. I describe a concept and then a number that goes along with that. But many of you may also be working with other advanced tools like ANSYS to create new components and then to export some sort of file that describes that. So in addition to just simple parameterized models, we can take a lot of file formats to describe the different types of models in your systems. So things like antenna gain patterns or the movement of platforms, the time history of their position and attitude and things of that sort. And then beyond these two static types of models, there's a lot of models that are interactive or executable. So if you're writing some sort of compiled code or some Python scripting, then you want to be able to take that model, embed it inside the mission environment, and take advantage of all the other things going on in STK to stimulate that model, let it do its calculation, and then return a result back to STK for that mission level analysis. So to that point, once you have all your different mission models inside the SDK environment, you now have access to all these different measures of mission effectiveness that are tied to those models. So where are you, where are the things you're interested in, and what are those relationships between them? So it's not just the SDK relationships of dynamic geometry, vectors, angles, things of that sort, the communications interactions, the EOIR interactions, but also anything that you have the algorithms to define as well. For example, we've worked with experts in acoustic propagation, which we were able to add to the SDK environment through these plugin points that we're describing. And then, of course, because you're not the only person in your organization working with SDK, you need to share these results with everybody else. So collaboration is a huge part of what the digital engineering environment is really all about. And then, of course, scalability. So there are a lot of complex calculations going on when you're trying to understand how an overall system of systems will perform in a mission environment. So we need to be able to scale these calculations and make use of all of the resources available to you, whether those are local machine resources or if those are cloud-based resources for parallel computing and things of that sort. We've already got that infrastructure in STK, so once you've added your model to STK, you can take advantage of all that framework as well. So let's talk a little bit about the rationale behind all of this. We've been working with customers for over 30 years now, and what we typically see is a very disconnected life cycle. When you're in the concept development phase, you're building all of these models and the background physics environment that those models live in. And then when those concepts get promoted into actual requirements and into an actual engineering design, we see that the industry tends to start over and now build new models with probably a little bit more complex fidelity. And then, of course, because of that, they have to reinvent all of the physics models behind those. So at every stage of the life cycle, we see people building new models and then having to rebuild the physics environment behind those. And so you're never really sure that the models you're using in this stage are accurately representing the concepts that came before. And then, of course, you're just wasting a lot of time rebuilding a lot of wheels. The other problem is if you're not actually doing a full mission simulation until later in the life cycle when you've got all of these different components starting to integrate together, you're not really going to find any sort of critical issue with your design until you put those simulations into play. So the problem here is that once you discover issues, you just don't really have any time to do anything about them. So instead of this disconnected lifecycle, what we're advocating for is a much more connected lifecycle, where the tools that you're using at the early stages of the concept design and the engineering lifecycle are reused throughout the lifecycle. So now you can take those models that you developed early on and then just add fidelity to the models. But the key to being able to do that is keeping the mission environment at the center of the entire lifecycle. So here on the slide, you see SDK is at the center of the diagram because every single one of these other tools that you're using, the ANSYS models, the sysml to describe your system, the Java, the Python scripts that are running individual components, you need those all integrated together in one common framework, and that's STK, where every one of those models can now talk to each other using STK as a common baseline for what's going on. So in the end, what that really buys you is a whole lot less work, much more ability to get to market quicker with your products, and then just much more confidence that the products you're delivering are going to meet the original objectives that you had. So enough slide work. Let's actually start to get into showing you how we actually do this. So I'm going to start off by bringing up STK here. So the types of models that I described, the first one that I want to illustrate is what we can do with just a simple list of numbers. So a bunch of key value pairs to describe different items in a scenario. So in this specific scenario, so far all I've added is a facility. And when I open up the properties, you can see here that I've defined the latitude and the longitude of this facility. So with just two simple numbers, I've already got some sort of model defined in my scenario. But today's video is not about going through the user interface to construct models. It's about integrating with STK and automating all of these types of models. So I'm going to take a quick step back and introduce you to a little project that the engineering team here at AGI has been working on. So over the last couple of months, we've been starting to identify utilities and code samples that we've been building up over the last couple of decades. And we're now hosting those on an Analytical Graphics Inc. GitHub page. So now the models that we've been working on and relying on are now available to all of our customers, either as functional tools that you can go download and start to work with right now, or as examples of how you can start that integration process. So to describe a little bit about what you're seeing here on this page, this is the main page of our SDK code example site. And you'll see here there are four main folders. You've got SDK automation. So that means you have the SDK application up and running, and you would like to use a script or some compiled code to send commands to SDK and make it do things. We've also got SDK engine applications. So if you don't want to have the SDK user interface as we've described it, but you want to build your own custom workflow on top of all of the engine components that are available inside SDK, then you can build your own workflow, your own user interface on top of the SDK engine that we provide. Now, if the SDK engine itself doesn't do everything you need it to do, this is where the SDK Extension Plugins come in. So now you can add your own custom code to the SDK engine, and it will be executed in process with the rest of that mission simulation. And then finally, SDK UI plugins. So this is now a way that you can still use the full-featured SDK desktop application, but also include your own custom user interfaces. So things like those custom workflows for the operational folks who just want to go through, do a series of things the same way every day, you can now customize that workflow and make it available directly in the SDK user interface. All right. So now that I've kind of introduced what's going on in the overall GitHub page here, let's dive into one specific example. So I'm going to go into the STK automation location and into the VB script directory. So pardon me for starting off with an archaic language example here, but I'm actually going to be demonstrating integration from Excel, which is using the VBA language behind the scenes in the macro. So again, let's go ahead and now look at this STK Excel spreadsheet here, which I've already got conveniently open. So what you'll see here is in my Excel spreadsheet, all I've got is a series of parameters. So I've got a variety of targets in my list that are only defined by a latitude and a longitude. And then I have a couple of parameters that define a satellite orbit state. So I'm going to go ahead and just click the Insert Targets button here in my spreadsheet, and you'll see that it's already creating every one of those 25 targets and putting those at the locations defined here in the spreadsheet. So let's go ahead and look at the code behind that macro. So very simply, all we're doing here is for each of the items in that data table, we're checking to see if the scenario already contains an object with that name. And if it does, it just connects to that object here. Otherwise, it will create a new target with that name defined in the spreadsheet. So once it creates that target, then it's going to use the API here to assign the location. So again, today's video is not necessarily about all of the API commands that are available to you. We have a lot of other tutorials that can start you out from scratch and teach you how to connect to STK and send a variety of commands to STK. But I just wanted to illustrate right here that automation is one of the easiest ways to start to send your information, your data, your models to STK. So if I flip back over here, not only can I insert all of these targets, but I can also insert a satellite, which now you'll see in my scenario as well. So at this point, I want to pause a little bit and just already illustrate that we've got a very complicated model here that's really only been defined by about 50 numbers. So already I can start to see where all of these objects are in relation to each other over time. So again, that dynamic component that SDK provides is really the thing that makes us stand out amidst all of the other simulation tools you could use. So, as I said, I've constructed a bit of a mission already. When can this satellite see any one of these ground targets? So again, from just the simple set of parameters here, I already have the ability to compute all of these visibility times. So here's just the times available for the satellite to see target number 1. I could easily automate that for all of the rest of the targets. And again, if you look at the macro that's provided in this spreadsheet, you can see what the code is to insert those satellites, to compute those axes, and capture those parameters to report them out. So I'm going to leave it at that with this specific example. But again, I started off with a pretty terrible language. Most of you are probably leaving VB script behind. So let's take a look at something that's a little bit more modern. So Python. Python is very big in the industry right now because of its flexibility and its availability. So here are a variety of different tools that have already been created using some Python scripting with STK. The example that I'm going to show here is the SDK metadata extractor. So the idea behind this script was we've been working with ANSYS a lot lately to understand how their detailed component analysis can be leveraged in our mission simulation environment. And one of the other tools that ANSYS has available is an SPDM tool called Minerva. So Minerva is going to host the workflow that helps engineers get work done, and SDK is just one of those tools. So after completing the work with STK, the Minerva system wants to understand a little bit more about what was done in that scenario, so that way it can categorize things. So from there, it wanted a bunch of metadata from the scenario. So I created a simple Python script that the Minerva application can call each time a scenario is submitted to that repository. So the SDK metadata extractor, if we look at the code here, we can see is going through each of the individual objects and then summarizing that STK object. So depending on the type of object, if it's a facility, we're going to capture the position of that facility and put that into the metadata. However, if it's something like a receiver, we're going to look at the type of the receiver, or if it's an antenna, looking at the type of the antenna. So when I go ahead and look at the output from a script like that, you can see here that it's not necessarily just exporting those numbers, but because I've put it into a script, I'm actually able to reformat that data in any way that my users want to consume that data. So in this case, we're exporting it as an XML file because that's how Minerva wants to consume metadata. Now, beyond just capturing the data values, one of the other things that this SDK metadata extractor script can do is export a cesium summary view of that scenario. So for those of you that aren't familiar with cesium, cesium is a WebGL 3D visualization tool. It was originally created here at AGI. The cesium team has now spun off as their own organization to address a much larger marketplace than the AGI organization, but we're still able to leverage the power of that WebGL display mechanism, which doesn't require an installation on anybody's workstation. So here, in addition to the XML that was exported to summarize my scenario, I can also look at this cesium file that was exported. And when I drag that into a cesium display, you can now see that all the components of that mission are represented here. Each of those targets, this satellite, and then even the access that's been computed between this satellite and the individual target that we're looking at here. So again, being able to capture all that information and represent it in whatever form factor is of interest to your customer or to your users. All right, so I'm going to go back to this scenario, and we're going to start to add a little bit of complexity. So again, what we've defined so far is just a simple parameterized model of the overall mission that this satellite is trying to do here. But in addition to just simple parameterized models, what I've often run into are complex data files that describe a model pretty completely. So when we're talking about data files that describe models, the first thing that tends to come to mind for me is GIS information. So what kind of terrain data are you using to describe what's going on in the environment around you? When it comes to terrain data files, just by showing the properties here, you can see there's a lot of different data file formats that are standard to the industry that we support. So the DEMs, the DMEDs, the DTEDs, all those different industry standards, we can already just import as they are. So if you have terrain data, we can import that. In addition to terrain, we also have 3D tiles. So if you're looking at sitting and building geometry, those can also be imported. For my case, I've already got, instead of just loading this into SDK, I'm going to connect to our terrain server, which actually has all of these different data files already hosted for me. So now I can just use that from the server-oriented fashion, and everybody in my organization now has access to that data instead of it just being local to my machine. Again, back to that collaboration concept we were talking about earlier. In addition to the terrain data formats, we also have a lot of other components in the environment around you. So specifically, when I'm looking here at the properties, we have the RF environment. So when it comes to how your communication is going to propagate from your transmitter to your receiver, we need to incorporate those propagation losses. So we can do that by just implementing, again, industry standard models here that are captured in standardized file formats. So atmospheric absorption, I could look at tropospheric scintillation, ionospheric fading, all these different kinds of things, building those into my model. For the aviation industry, if you're looking at our aviator module, what that does is it tells you how a specific type of aircraft will perform given its lift and drag curve. But in order to do that, you need to have the atmospheric characteristics to interact with the properties of the aircraft. So here on the aviator environment model, you'll see that we can link up to standard NOAA services as well. So again, depending on the type of environment data you have, more than likely we have a standardized format that we already work with, and your data is probably represented there, so we can just directly ingest it. Now when it comes to the other types of objects in this scenario, or the other types of GIS information, it's not just the terrain data, but also things like shapefiles to define where specific types of objects are in the scenario. One of the things that I'll pull in here to my scenario is, instead of the shapefile, I'll look at a little bit more common file format that you see being created out there, and that's now the KML standard. So I'm going to take this US airspaces KML, just drag and drop that into the STK window, and you'll see that the visualization here is already available. So if I zoom in to my current location, I can see what airspaces are around me based already on the KML data set imported directly. So as you're seeing it right now, it's just for visualization, but that's not all that we can do with that. We've got this handy Get Info tool. So now I can select any element in the KML data set, interrogate that, and even import that directly to my scenario so that I can continue to do analysis on that later. And then, of course, as I mentioned, when it comes to visualization, if you have any sort of imagery that's also defining what's going on in your scenario, if you've got aviation maps, if you've got, again, more GIS information about pipeline locations, things of that sort from an imagery standpoint, we're capable of working with pretty much any standard tiling service out there. For example, we've got Bing Maps natively integrated into STK, so that's nice. But there's a lot of other standard services available that we don't have natively integrated. So let's take a look here at anything that's available as a web map service. In this case, I'm going to link to one of my favorite services that's providing NextRad weather radar data. And that's coming from a WMS service hosted at Iowa State University, which is my alma mater, so nice job, guys. So I'm going to go ahead and add that WMS layer to the scenario here. And now you can see that I've imported all of the weather data across the US. So this is good for any sort of tiled data service that you have available in your organization. So the last type of data files that I want to describe are not just the type that describe the environment, but let's look at the things that define how individual objects behave. So for the space community out there, there's a lot of different types of files that describe a satellite state. So if I drop down the menu here, you'll see something like SGP4. So for anyone that's ever worked with the standard TLE catalog, those individual sets of TLEs are all propagated with the SGP4 propagator. However, if you're looking more at a lot of the astronomical bodies out there, the comets and the asteroids, things of that sort, you'll typically find those published in a SPICE data file. If you're looking at GPS information, almanacs, SP3 files, if you're looking at some of the geostationary satellites, looking at 11-parameter satellite state formats. So a lot of the standard formats that you're using throughout the industry, we already natively support in STK. And now, let me go ahead and illustrate loading some of those into STK. So on this LEO satellite, I'm going to go ahead and add a transmitter object. So now, again, on this transmitter, we have all these different types of transmitter models that we can create. And when we want to define an antenna, there's a bunch of standard antennas that we support here already. And then if you're looking here at each of these individual file formats, one of the newest formats that we support now is the ANSYS FFD format. So now, if you're working in ANSYS HFSS designing antennas, you can directly export the definition of that antenna, and it will be available to import directly into SDK. So this is brand new with SDK 12. So it's great that we can connect to a native ANSYS format right now, but when I first started working with our partners at ANSYS, we didn't support this file format yet. So this is a very common problem across the entire industry, is a lot of different locations will build their information into proprietary formats. And so no matter how many file formats I support from an industry standard perspective, there's probably going to be data available to you that doesn't fit one of the industry standards. So to handle that, what we've done is we've created a lot of generic file formats that are really only useful to STK, but through the STK help system, we've defined what all of those file formats are and how you can create those. So depending on the data you have available, if there isn't an industry standard format for that data, or if you just don't have your data in that industry format, then you can check all of the other external file formats available here, and you can transfer your information into a format that we've already provided. So again, just providing you an avenue to get that information into STK. To show you that example, again, before I had the ANSYS FFD file format available, I would work with our partner to create a report in the ANSYS tool that would export the information I needed for STK. So here we have an antenna gain pattern. And that means at any individual angle direction, you get a gain value that tells you the relative strength of how that transmitter or how that antenna will radiate the RF signal from there. So I've got all this information that tells me the gain pattern. But this is not a file format that is an industry standard STK can read, and it's not in one of the STK file formats. So what I was able to do is take that, convert it into what we call the .pattern file, and really all I had to do was, instead of being a CSV file, this is a tab-separated file, and then I had to add just enough information in the header to let STK know how this data was structured. And again, if you're interested in how to assemble any one of these data files, please see the STK help under Create and Import External Files. And again, this will list all of the different file formats available to you, and will even provide you examples of each one of those individual file types. So now, once you understand what's going on in the header, you can apply your data, and again, now your data is directly available inside STK. So let's show importing this specific model into STK. So I'll be using that external antenna pattern, and I'm going to link to the model file that I have available. And then, of course, because it's STK, I'm going to go ahead and turn on the graphics so we can see what that looks like. So now, in my 3D window, I'm going to zoom to that satellite. And what you can see here are the numbers that were previously in my data file have now been imported to STK and translated into a functional antenna model that I can use for analysis in STK. So now, with my transmitter, I can compute access to another RF object, in this case a receiver here on my facility, and I can compute that link budget that tells me now not only whether or not one object can see the other object, but what is the quality of that interaction. So I can look at something like the bit error rate over time or the carrier to noise ratio, and instead of looking at it as a data file, I can also look at it as a graph. And from here, I'm capable of zooming in on any one of these individual passes, looking that in as much or as little detail as necessary for my analysis. And now I can see here how that's changing over time, all based on the model that I added to this scenario. All right, so to recap, what we've done so far is we've constructed a full scenario out of a lot of different types of models. So we started with the parameterized model of where our targets are, where our satellite was. We then imported a lot of other data to define the environment around these objects. Where was the terrain? What shape did it take? Are there any regions of interest close to these objects? What's the RF environment looking like? We then extended beyond that and built more fidelity onto the antenna gain pattern and how that interaction happens. So now what I want to talk about is going beyond these static data models and start to talk about some of the data models that you might have that are executable and that are more dynamic. So again, I'm going to take us back to the SDK code examples GitHub page. And in this case, I'm going to talk a little bit about these SDK Extension Plugins. So there's a lot of different places that SDK has plugin points that you can plug in your own logic to define how something is computed in SDK. So again, I'm going to take you back to the SDK help just to highlight what those plugin points are. So first off, there's two different methodologies you can use to get your dynamic models into SDK. So if you just like to write scripts, VBScript, Python, MATLAB, things of that sort, then these are all the different plugin points available for scripting. At the top, you'll see access constraints. So anytime you have visibility between two objects, you can tie into that calculation, you can describe what visibility means. So does that mean line of sight? Does that mean electro-optical visibility? Does that mean RF visibility to a radar? Or as I mentioned earlier, does that mean something like acoustic detection? Other things, other interactions that SDK may not natively compute. You'll see a lot of things in here about astrogators, so getting into how we actually propagate maneuvers for satellites and how we define the engine models and the performance characteristics of those satellites. Another segment down here are all the different communication plugin points. So if you're defining transmitters and receivers and the interactions between them, we have a lot of different ways that you can inject your logic there. Same thing with radars. And then down here, vector geometry. We frequently refer to this as kind of the Lego building blocks of STK. The points, the vectors, the planes, the angles, all of those underlying dynamic geometry components that go into constructing where things are and how they move. You can plug into that system as well. So these are all scripting plugin points where you can just write, again, just a simple script, put it in the right place, SDK will know how to load that for you, and it'll be available directly in your mission simulation. If you're the type of person that spends more time writing compiled code, .NET or COM-based engine plugins, then there's a slightly different set of plugin points. For the most part, these overlap, but there are some places that you can get to with scripting versus COM components that are slightly different. So again, you'll see the access constraint plugins, those astrogator engine models, the radar and the communications segments, and then here, one of the components that you can do in the CommBase plugins is to tie into the graphics engine of STK. So if you want to build your own shapes and volumes and things of that sort in the 3D graphics window, you can plug into all of those interfaces right here and build your own graphics elements in addition to what STK already provides. From here, I'm going to go back to that GitHub page that I started off at. And now we're looking again at those SDK extension plugins. And you'll see that there are a variety of different C# access constraints. And the one that I'm going to illustrate here today is this object detection example. So I built this plugin just purely as an example of connecting to a third-party library, a DLL, and accessing functions from that from within the STK plugin architecture. So again, you're welcome to visit this page, download this code example, load it up on your own, and then make changes to this code segment so that way it fits your own code, your own plugin model needs, and you can now actually reuse what we have here as an example. So if I open up the code under the hood here, you'll see I'm using Visual Studio. I've loaded up the example. Over on the right, I've got two different projects here. There is the STK12 access constraint plugin. So that's the thing that's actually going to be compiled. And then STK will load this and execute it at every evaluation step. So you'll see here, I'm looking at the evaluate method. There's a couple of other methods in the interface that you've got to support to do the initial setup, connecting into the STK environment. But the real meat and potatoes of what's going on is down here in the evaluate segment, where in this case, I'm not really sure what this payload does. This payload detects things. And for those of you out there, you guys are building systems that are doing things that we can't possibly imagine. So this plugin point allows you to take any logic that's defined within your custom payload and now allow STK to determine what that target detection probability is. And again, based on the logic you have defined in your DLL, we're just accessing that. So from here, this compute target detection probability requires a few input parameters. So it's looking for the relative position of the target object from the payload, and then it's also looking for the sun vector. To me, it doesn't really matter what the code on the other side is doing with these values. I just know that these are the types of values that it needs to do its work. So from STK, I'm able to capture what that relative target position is, and I'm able to capture things like the sun position from the sensor perspective. I could get to pretty much anything you can imagine as far as relative position, orientation, and interaction between two objects in a scenario. So just assume you can get to any component. If you have any struggles with that, that's what we have tech support for. They would absolutely help walk you through how to get to any of those mission simulation characteristics in this plugin environment. But again, I'm now requesting information from the plugin at each time step. So let's go back to STK and actually create that sensor on our satellite. So from here, I'm going to go ahead and add a sensor to that satellite. And when I go into the sensor properties, down here under constraints, you'll see a plugins segment. So from here, you'll see I have an object detection plugin available to me that I can enable. And now, when I compute anything, so I'm going to now compute access from the sensor to that target again. I'm going to go ahead and bring up my report and graph manager, and I'll look at the actual detection values here. So what you'll see here is the probability of detection during all of those access intervals as reported by the plugin. So I can zoom in over here on one pass, very much like I did with the communications results that we had, and I can see how that varies over time. So perhaps I'm only concerned about passes that have a greater than 70% probability of detection. When I look at the overall results here, what I can see is that there are 1, 2, 3, maybe 4 passes out of the collection that won't ever cross that 70% threshold. So now, with a very simple plugin model of my sensor payload, I can already see that half of the access opportunities are not valid, which means I either need to go rework what's going on in my payload capabilities, or I need to revisit the requirements of my system and just help the people designing those requirements understand what the actual capabilities of the systems are. So again, just pointing out how quick and easy it is to get to some overall mission effectiveness capabilities here in STK with all of these integrated models. So the last component that I want to illustrate here is back to the operational user. So we've been talking a lot about the engineering models that you're going to use through the concept design phase, the engineering design phases, maybe even through the test and evaluation stages as you're trying to see how all these components work together. But the real value of a common mission operating environment like STK is the same models that you use to define the vehicle movement, orientation, performance, and sensor performance can also be used directly in any sort of operational use case that you have as well. So as I mentioned earlier, we have, again, back to our code examples here, we have UI plugins. And again, these let you build new user interfaces in STK that are now accessible to any user of that application. So in here, one of my favorite plugins is the Great Arc plugin, which allows you to now construct vehicle routes from a plugin algorithm that is going to do search patterns and connecting the dots for a variety of targets. So again, feel free to download this plugin, add it to SDK, and use it for your daily tasks. So let's say that it's not just a satellite mission that I'm interested in here, but also an aircraft mission. And so to work with some of the data that we've already imported into our scenario, perhaps I want to do a mission plan from the facility location I've defined here to go search that region that I imported from my KML dataset. So now I'm going to go ahead and insert an aircraft from a search pattern. This item on the menu is not in your STK guaranteed, unless, of course, you've already gone through, downloaded that plugin from the GitHub page and installed it in STK. This is what I mean about integrating directly into the SDK user interface. So now I can insert an aircraft from a search pattern, and it's going to ask me whatever custom parameters are available to this user interface. In my case, let's go ahead and say I'd like to do a fixed number of passes. We'll do 10 passes over this region. I'm going to start off at the facility. I will then do a north-south raster search pattern. I could easily change that to an east-west raster search. And then after that, I'll fly back to my facility. I can choose a couple of parameters here, like the speed. Maybe I'm only flying at 80 knots, and maybe I'm only flying at 7,000 feet. Smaller aircraft, something of that sort. So now, when I go ahead and create that vehicle, I'm going to see a new aircraft route pop up in STK that now defines the behavior of the system that's available to me. And again, integrating it directly here. So now I can use all those same components in my scenario that were used for the satellite analysis. I could just as easily attach those transmitters and receivers defined from external models and start to do the analysis of how well this aircraft is searching this region. And again, having that all integrated into the operations environment that's leveraging all of the power of every engineering model that came before in the life cycle, and continuing to move those forward and taking advantage of those all the way through the operations phase and then into the sustainment and the next round of iterations to improve on those capabilities. So to summarize, let me just go ahead and go back to our whole world view here and point out that I've got a lot of different models integrated into this one simple scenario. I've pulled data from Excel spreadsheets. I've integrated industry standard data formats from KML, terrain and imagery, and even WMS weather services to import all of that data into the scenario. I've even linked to complex analysis from external tools like ANSYS. Then I've integrated in a custom plugin model based on compiled code developed by a third party, in this case in C#. And I've put all of that into one common interface that now lets every single one of those models play off of each other. So that's a very important point that I want to reiterate here, is that it's not that I can just take a variety of different ANSYS models and play them against each other. It's not that I can just take a variety of different data file formats for communications and work with those. I'm doing a lot of mix and match here. I'm taking some numbers from a spreadsheet, I'm taking some data files from ANSYS, and I'm taking some plugin executable code from some random third party, and those are all integrated into one common mission analysis framework that really lets you understand how all of these systems will behave and how they'll play off of each other. So again, just want to jump back here to this slide to finish off and actually show that we have integrated all of these component, subsystem, and system level models into the SDK mission environment and providing you that understanding of how your system will actually perform such that you can now understand what's going to happen in your system at a time frame in the project lifecycle where you still actually have the ability to do something about it. So in the grand scheme of things, this is digital mission engineering, having all of your models in one common mission environment so you can truly understand the capabilities you are designing. So thank you very much for joining us today. If you have any questions, please don't hesitate to reach out to our technical support department, support@agi.com. They're very friendly, knowledgeable people that will help you get to this vision much sooner. So thanks again.